Hello, and welcome to today's webinar from Ricardo North America, Solutions to Automotive Thermal Challenges, with a particular focus today on the passenger car of tomorrow. My name is Chris Brockbank, and I'm Vice President of Technology and Strategy here at Ricardo North America. If you've listened to our previous webinars, you'll understand this is not a North American accent I have, but I'm working over here. I've been working for Ricardo in the North American office now for 6 years. Prior to that, I was working in the German office, and prior to that, the Ricardo UK office. I originally started at Range Rover in the UK and have a background in electronics and powertrain through to all areas of the automotive vehicle. I'd now like to introduce the rest of the team, starting with Dr. Cedric Rouard.
Thank you, Chris, for your introduction. And I'm Cedric Roux, and I have a French accent, as you can hear, working in Ricardo, UK. I'm global technical expert for thermal systems. I've worked in the domain for the last 20 years in passenger car, but also since I've joined Ricardo in the last 12 years on commercial vehicles off-highway, marine, and also aviation more recently. And I will hand over to Pete now. Thank you.
Thank you, Cedric. I'm Peter Fussy, and I'm a technical authority in propulsion control. I have over 20 years' experience in developing advanced control systems for powertrain and vehicle applications. I'm currently developing new solutions in connected control and hybrid and electric vehicles. And finally, over to Dave.
Hi, thank you very much, Peter. My name's David Barnes. I'm Chief Engineer in the Technology and Strategy Group, working for Chris Brockbank. I've been with Ricardo for 25 years now. During my time here, I've touched most parts of the business. So with that, I'll hand back to Chris. Thank you very much.
Thank you, gentlemen. So before we dive into the presentation today, let's just do a little bit of background on Ricardo for those of you who don't know us, and a reminder for those of you who do. So Ricardo is a global engineering and environmental consultancy, and we specialize in transport and energy and scarce natural resources. Our vision is to create a world fit for the future, and our work extends across a range of market sectors, from passenger cars to commercial vehicles, rail, defense, motorsport, even power generation and government projects. It's definitely a comment that working at Ricardo is not something that's going to make you bored or repetitive. You could be working on so many different products, so many different technologies, all of which are cutting edge as we go through our careers day by day. We have a century-long track record delivering projects rich in innovation and technology. And through our multi-industry knowledge and expertise, we are uniquely positioned to handle our clients' toughest strategic and operational challenges. And across everything we do, and in every assignment we undertake, we remain committed to the ethos of our founder, Sir Harry Ricardo. He was one of the most innovative mechanical engineers of his time, and in 1915, he set out on a mission to maximize efficiency and eliminate waste. And that is what we keep in mind through everything we do to this day. So there is the vision, to create a world fit for the future. And how are we going to deliver that? Well, the 6 areas on the outside of this vision diagram show you, from rapid urbanization and air quality, climate change, to energy security, sustainability, connectivity, natural resource and global stability. And the topic today is of particular interest in virtually all of those areas, the thermal aspects required. As we increase the work of a vehicle, be it a car, be it a truck, train, thermal is becoming more and more important. Not just for cooling the powertrain, which is the first reaction, but for all the ancillaries, for all the sensors and actuators that are required, for all the electronics and compute that is needed, and actually through to, of course, looking after the passengers and the operators. Here in Ricardo North America, how do we support that global vision? Today, new mobility is still in concept. But in some point tomorrow, and that's the point we're working to, new mobility will be at scale. And this is the chasm that we are currently crossing. And we're basing our route to that, we're integrating a path to this better mobility future. We're basing it on certain principles. You see on the slide, advanced propulsion, software and controls, and critically thermal management, that'll get us to this zero carbon mobility. Here in Ricardo North America, we have a footprint that is spread across the country, from our head office in the Detroit Technical Center and satellite in Chicago to 2 areas in California, our Innovation Center in Silicon Valley and our Technical Center recently opened in Southern California. So we are geographically aligned to our market and technology offerings, and we have deep expertise, but we're also nimble and we're very agile in our developments. We've recently partnered with an Argentinian software development house to provide an example of that agility. So without more to do, I'd like now to hand over to Dave Barnes, who will take us through the meat of this webinar today. Dave.
Thank you very much, Chris. As you're probably all well aware, we have a number of challenges that are facing us around emissions, autonomy, the development of battery electric vehicles. All of those have impacts onto the way we design vehicles, particularly vehicle thermal systems. Efficiency of these vehicles is becoming more critical as we transition into battery electric vehicles. The availability of free heat from internal combustion engines drives us towards more advanced solutions for thermal management. So we'd like to talk a little bit more in the next few slides as to how we think we can improve on the current situation. Before we get too deep into this, I'd just like to refresh everyone's memory as to how we classify types of hybrid electric vehicles. We use the term XEV generically to include anything with an electric-based propulsion system. But those are divided into several different classes. You have charge-sustaining vehicles, which are called HEVs. You have PHEVs, which are plug-in hybrids, so they have the ability to draw power from a grid, as well as being recharged by the engine. You've got range-extended EVs or REEVs. So that has something like a BMW i3, where you have a small engine that can power the car for a limited amount of time. And you've got full battery electric vehicles, which have no internal combustion engine at all. And then finally, you have fuel cell electric vehicles, which use a fuel cell in addition to a battery to actually power the vehicle. There are significant downsides as you move into a battery electric and PHEV range of vehicles, particularly ones, PHEVs and HEVs, when they're running in electric mode. You lose all of this free heat. So it used to be that heating anything in the car was easy because you had free heat from an internal combustion engine, which was otherwise just going to waste. Air conditioning was the primary energy use over and above the keeping the vehicle moving forwards. As we move into a battery electric space, we see that heating actually becomes more important than cooling in terms of the energy that's used. It takes more energy to heat stuff than it does to cool it, particularly for the cabin. It flips around a little bit on batteries because we have to say, all right, if it's really cold outside, you have to preheat the battery before you can charge it quickly. And then once it's charging quickly, you then have to cool it. So the battery has 2 different sets of problems. We can mitigate some of the cabin heating using direct heating, things like seat heaters, steering wheel heaters. So you're heating the surface that the occupant is sitting on rather than the air around the occupant. That's proven to be an effective way of minimizing the heat used. But even so, you still are stuck with PTC heaters, which are large consumers of energy and have very low coefficients of performance. So we try, if at all possible, to minimize the use of direct electric heaters. So as you can see from this slide, we're trying here to get some overview of the complexity, the relative complexity of cooling circuits for internal combustion engines and hybrid electric vehicles. So the typical internal combustion engine vehicle, you can manage with a single cooling circuit. Everything operates at a similar kind of temperature. The waste heat has enough of a delta T that it's usable in order to heat the cabin. And then the only other loop is a refrigerant loop, which is used to cool the cabin and sometimes used to cool some of the other components, but principally it's a cabin cooling device. When you look at a hybrid electric vehicle, you see that Actually, now we need two separate cooling loops because the electronic components cannot operate at the same temperature as the engine does. So you will cook the inverters and the motors if you try and run them at the 90 degrees C that an internal combustion engine runs at. So now we need to split those two coolant loops. And we see a similar example on the right-hand side of the slide, which is a range-extended EV, which again requires multiple thermal loops. This one is actually from an i3 BMW, and they're using the refrigerant circuit to actually cool the battery. But you can see that as you get more into a BEV range, then the system does get more complicated to optimize. I'd like to now hand over to Cedric, who will cover in a little more detail some of the individual component optimizations that we're able to achieve before we start building system-level models. Cedric, over to you.
Thank you, Dave, for your kind introduction. And I will talk about now our integrated thermal management solutions for electric drive and transmission. So when focusing here on the evolution of the electric drive unit, EDU, we have plenty of acronyms. We have also DHT, dedicated hybrid transmission. And from the bottom of the slide, we start with the separated configuration between electric motor, power electronics, and transmission. And we can find nowadays more integrated solutions where we have all the components together nicely packaged into the transmission casing. When we do that, we in Ricardo have developed a solution on a European funded project called EcoChamps. We cool all the components with the transmission oil. The electric motor, the power electronics will be oil cooled. That is one possible route that we have selected. Others, like on the slide mentioned here, Audi have selected the route of going purely with the ethylene glycol water solution. But we have developed a multi-speed electric drive unit with this oil-cooled solution, which we think is quite now a groundbreaking technology. Focusing on the electric motor and the thermal management of its cooling method, we highlight here where the heat sources are and what is the mechanism of the heat transfer from the stator going into the cooling jacket, conventionally using a stator cooling jacket with ethylene glycol water, or also how to cool the permanent magnet inside the rotor. Nowadays, we use oil cooling. So we show here different examples of oil cooling methods with oil dripping on the stator, oil jacket inside on the stator periphery, like the Tesla Model 3. Oil dripping on the end windings, oil jet cooling on the winding coil, and oil flow inside the stator slots, oil flow through the rotor jacket are the last two, number 5 and number 6, that are quite innovative and require a lot of activities between electromagnetic analysis and designer and the thermal analysis and engineer. So we have different tools and techniques to support this type of development, starting from 1D lumped capacitance model, going through 3D CFD simulation, and 3D CHT, conjugate heat transfer, but also 3D SPH, a lot of acronyms, I'm afraid, for smooth particle hydrodynamics. Now we have the evolution for the power electronics. The same as for the electric motor, we have the heat dissipation, the thermal management solution, how we extract the heat from the chip, which could be silicium, silicium carbide, or gallium nitride. And in the last 20 years, we have seen a trend to increase the heat flux density from roughly the 100 watt per square centimeter up to 400 watt per square centimeter. By doing so, for the thermal engineer, we have now a challenge in order to extract the heat from the chip in an indirect way at the base plate level of the inverter using conventional method cooling jacket with pin fins, serpentines, a way to increase the heat transfer at the base plate level, including also impingement jet with ethylene glycol water, to a more integrated solution where we cool directly the chip itself using dielectric fluid, the same potentially oil as the transmission lubrication and the electric motor cooling. So now focusing a bit more on the oil cooling again, but now dedicated for the power electronics, we can envisage the oil to cool the base plate using impeachment jet. We need that jet effect because the heat transfer coefficient with oil is always lower than with ethylene glycol water. And also, as I mentioned previously, the oil directly cooling the chip at the core of where the heat is generated. So that is under development for the wide bandgap applications, gallium nitride and silicium carbide in Ricardo. Another example now of our CFD analysis, CHD analysis. Here it's cooling the base plate of an inverter using impeachment jet, submerged jets of oil, using transmission oil, that was developed on EcoChamps project, a European funding project, where we developed that solution for a BSG application of 48 volt, 25 kilowatt. The idea was to have a cooling jet at each position of the chip on the other side of the base plate, or here, the other side of the PCB. So that means we were having one jet per chip. By doing so, we are able to control very well the temperature of the chip. Below, here in this case, with MOSFETs, 125 degrees Celsius max temperature for the junction temperature. And also to have a very well integrated solution because we are using an oil that can be using also the transmission oil, and the electric motor is also cooled with the oil. So that was developed already a while ago, and now we use the same technique for electric drive unit for battery electric vehicle on a multi-speed EDU that I've mentioned previously. Moving on now to the battery, we have several cooling methods that are summarized here on the table, starting from air cooling solution, going to liquid ethylene glycol water using cold plate, side cooling or bottom cooling or top cooling, refrigerant cooling in the cold plate using directly the air conditioning refrigerant, and also immersion direct cooling of the cells with the dielectric fluid. In yellow, you see at the top of the table the C rate, continuous C rate that can be used on a battery electric vehicle during fast charge. Air cooling can go up to 1.5 C for several tens of minutes. The cold plate using ethylene glycol water can go up to 3 C. And this is the solution that is used nowadays on most of the battery electric vehicle when they want to charge at more than 150 kilowatt and up to 270 kilowatt on the Porsche Taycan. They use a bottom cooling plate for their Porsche cell and up to 2.3 C for 22 minutes. That's the benchmark of the shortest charging time for a battery electric vehicle. Going to the refrigerant, we have only 2 C maximum, and for immersion, we can go up to 6 C in single phase without going into phase change using chemical fluid for above 6 C. We show also on the bottom of the slide the comparison of the cold plate versus the immersion cooling in our Innovate UK funded program called ICOBAT for immersion cooled battery, another acronym, I'm sorry. And we developed that solution, started to develop that solution 1 year ago with other partners such as MNI for the dielectric fluid and WMG for the test of the module that is using cylindrical cells. So we compare the solution of cylindrical cell cooling with cold plate, with immersion cooling, and the graph highlight the benefit in terms of cooling performance, where we see that with the immersion, we can be below the maximum temperature of the cell, which is 50 degrees Celsius here. And also we can be cooling down quicker the cell after the fast charge period, which is here below 10 minutes. So roughly it was 4.3 C that was used constantly during that fast charging period. So once now we have highlighted the subsystem cooling methods using mainly oil cooling, dielectric oil for electric motor, power electronics, and battery, we will now introduce the overall cooling system. Going to the next slide, and we will present our approach using model-based development approach and a reduced order model that my colleagues will present later. So here we highlight the system complexity by having different components operating at different temperatures, from the engine when it is a hybrid vehicle, but it could be also a fuel cell, going to an electric motor, inverter, battery, and cabin. We see different green area where we have the nominal operation in terms of temperature. The battery is a bit the same as a second or fifth passenger on the vehicle on board, because it operates at the same nominal temperature as the cabin. This difference of temperature is already highlighting the complexity we are going into. And then after, we can also develop solutions to reduce the energy consumption for heating or cooling all the components, depending on the driving conditions and the duty cycle. And that will also increase the complexity. So you see an example at the bottom of the slide showing how we use multiple way valve, 4-way valve and 3-way valve, to couple or uncouple the cooling circuits, having the low temperature circuit in blue of the electric motor, the power electronics, the engine in red, and the battery with the air conditioning system in green and blue respectively. So we have an opportunity to reuse the waste heat from the electric components to support the cabin and battery warm-up, but also the engine warm-up when it is a hybrid. We have also development of heat pump system, direct or indirect, on the air or the coolant respectively, to improve the EV range when we are not using, or we try to reduce the use of electric heaters. And also different examples that will be presented later of recirculation strategy in the cabin in order to reduce the energy consumption required to keep the cabin cooled or warmed. So those are opportunities to develop new cooling architecture and control systems that we will see in the next slide. I just mentioned the heat pump solution to replace the electric heaters. We highlight here that we can have different heat pump solutions on the top left corner. Direct heat pump when we have all heat exchangers on the air side, or indirect heat pump when we have all the heat exchangers or some of them on the coolant side. There is no one best solution of heat pump system for all automotive applications. However, there is less and less heat available from powertrain to heat up the cabin and the battery. On the top left corner, you see the evolution of the waste heat from conventional ICE to hybrid and to battery electric vehicle. So this is why we require electric heating system or support of the lack of waste heat that we have from the powertrain. Based on the heat pump coefficient of performance, usually higher than 2, where actually an electric heater will be just below 1, we can assess the EV range benefit in cold conditions. The example on the right-hand side, top right-hand side, is using input data of the electric power requirement for heating a cabin of an SUV, and also the cooling requirement, but that's not the purpose of this slide. So this is the amount of electrical power that is required to maintain the cabin comfort. On a typical electric SUV, the range can be impacted up to 30%. It is the green graph using the electric heating system. So only 70% of the range is left when comparing the range without the use of HVAC system at -20 degrees Celsius. The simulation results present also that the heat pump, direct one here, can operate down to -10 degrees Celsius, and at -10 degrees Celsius, a heat pump with a COP of 2 will impact the range by 15%, and with a COP of 3, only by 10%. The drawback of the heat pump using 1234YF as refrigerant is that it cannot be used efficiently below -10 degrees Celsius. The issue is the mass flow rate of the refrigerant that is too low, and the coefficient of performance that is dropping very quickly. One of the possible solutions to mitigate that issue is to have CO2 or 744 refrigerant heat pump system that can enable to go to -20 and even -25 degrees Celsius when it is indirect heat pump to operate and not require any form of electric heating system anymore. One OEM will have a solution on the market very soon in the next year. We talked about, on the next slide now, we talked about the different architecture of cooling circuits. We mentioned quickly the architecture with the multiple wave valve. So we give a name to that. So multi-temperature cooling circuit, MTCC. This is how we define the evolution from separated cooling systems when the low temperature, medium temperature, high temperature are totally separated. And now when we can combine all of them using multiple wave valves. That is the trend we see also on the market. You have examples now on Jaguar Land Rover I-Pace and model Y from Tesla. The aim of this MTCC is to improve the EV range by up to 20%, combining the effect of the waste heat from the electric components to warm up the cabin and the battery, and also the effect of the heat pump instead of using an electric heater for cabin and battery heating. When focusing on a hybrid electric vehicle, we can also gain 1 to 2% fuel consumption improvement by using the waste heat from the electric components to warm up the engine in cold conditions. On the next slide, we also highlight that this multiple temperature cooling circuit architecture can be used also for fuel cell electric vehicles. On the right-hand side, we have an example of totally separated, again, cooling systems, low temperature in blue, the fuel cell in red, and the battery with the link with the air conditioning system if it is a liquid-cooled battery. The fuel cell system has a different feed from those other circuits, the low temperature and the battery, because it uses deionized water. It can have deionized water with ethylene glycol, but it cannot be mixed with the ethylene glycol water circuits or, of course, refrigerant circuits. So the idea when we want to combine them is not only to use valves, but heat exchangers between the circuits. So this is what is highlighted on the bottom of the left-hand corner, where we want to use the waste heat from the electric components to warm up the fuel cell, and not only the cabin and the battery, but also to extract the heat from the fuel cell, which has a major challenge in terms of cooling performance, and remove that heat to the other circuits that might not be at their maximum of their capability. So this idea of combining the circuits are mainly to benefit for the cooling aspect and also the heating aspect. So nowadays we talk about an octopus when we see this type of complex architecture on fuel cell vehicle, and we have developed that for different applications, passenger car and also a heavy duty truck, especially for projects in California funding with our US colleagues. Finally, when we are going now just on some examples of the heat pump systems and the evolution, we have tried to highlight here some of the benchmark that we have done in Ricardo, how the heat pump is operating, and if it is using the waste heat from the electric components, and if it is direct on the air side for the condenser and the evaporator, or indirect, having the condenser and or the evaporator on the liquid side. So you see from the Volkswagen e-Golf going to the Audi e-tron, BMW and Toyota Prius Prime, PHEV, the different heat pump system on the air side mainly, and some of them using the waste heat from the electric components. Focusing also on the battery electric vehicle Renault Zoe and Nissan Leaf, they are using direct heat pump with no reuse of the waste heat for now. But we see now the evolution with the Jaguar I-Pace and the Model Y from Tesla, which are having indirect heat pump, reusing the waste heat of the electric components. So those two certainly can get into the 15–20% improvement in EV range when using this type of architecture versus pure electric heating system. I will now hand over to Dave for the optimization of the multi-circuit solution. Thank you.
Thank you very much, Cedric. I'd now like to spend a little bit of time explaining how Ricardo's integrated thermal management approach and toolset can be used to drive increased efficiency at a vehicle level. Ricardo's integrated thermal management system, ITM, is primarily used at a system development stage in the process. Its ability to pre-check configurations and allows you to do a large amount of system optimization ahead of final component decisions. So you can do a lot of what-if scenarios before you ever have to build a prototype and test it. So the left-hand slide gives you an idea about where ITM is applied in a typical system V. vTherm is the name that we have for our tool set for doing this evaluation. But using this tool set at an early stage in the vehicle development process allows you to balance the thermal requirements across multiple systems whilst minimizing the cost for cooling and heating hardware, and then evaluating your options for reusing waste heat and storing waste heat. It also allows you to optimize the use of auxiliary components such as pumps, fans, valves, and compressors. On the right-hand side, you can see a very high-level example of how this process is applied to a battery electric vehicle. Using this process, we're able to improve EV range by up to 25%, depending on the cycle and the ambient temperature, and then do a much better job of managing the package of all these components so that we're doing the trade-offs between package cost and engineering capability correctly. So the first thing we have to do with an MTCC simulation model is we have to build a high-fidelity plant model. So this is comprised of a combination of AMISIM and Simulink models, which reflect at a very high level of fidelity the response of the system to various inputs. So we'd have cabin, battery, low temperature circuits, high temperature circuits, a control backbone that actually interacts with all of those, and obviously things like powertrain and e-machine models. So you can get a bit of an idea here about how these things are all constructed. These are all 1D lump mass models, but they all join together. So we're not analyzing anything individually at this point. We're joining all the pieces together so that the responses can be mapped across multiple systems. And then we feed that with test cycles and use cases in order to establish the response. So this next slide just gives you a few examples of the construction of some of the individual component models that are used to build the lump mass capacitance model of the whole vehicle. As you can see, we're up in sort of steps 1 and 2 of this process. The next thing we have to do after we built the lump mass model is to verify it against, or to verify a baseline condition against the actual test vehicle. So here's an example that we did on the Connect HEV Ricardo PHEV demonstrator. We ended up putting about 111 temperatures and pressure measurements. Then we drive it over a number of different test cycles and record the response of the baseline system to the test cycle. You should note that at this point we haven't made any changes to the actual vehicle. We're just looking at the baseline system in order to get a response that we can correlate our high fidelity model to. Once we have the baseline data, we can correlate our plant model against this data. So what you're looking at here is a cabin temperature model, which uses about 10 independent variables in order to try and match what the model does to what the vehicle actually did. So this is 50 kilometers an hour EV mode at minus 5 degrees Celsius ambient temperature with a 1.5 kilowatt PTC heater. Once we have the 3D model correlated to the baseline data, we can't really use that 3D model to run in real time on the vehicle. It doesn't run fast enough. So we have to actually get that into what's called a reduced order model in order to allow it to run in real time on the vehicle. There are a number of different approaches that we use to do that. It's very system dependent, but the idea is to get a real-time core which loses a little bit of fidelity but allows the control system that we'll talk about shortly to respond in real time to the inputs that are being fed to it. So this slide shows the results of the 2 steps that we've carried out here: the correlation of the high fidelity plant model, the reduction of that plant model to the reduced order model, and also the correlation of the reduced order model back to both the high fidelity and the vehicle level. So we can see here that we're able to get within 4 degrees C for the between the vehicle model and the plant model, and then about 8 degrees C back to the vehicle model from the reduced order model, which is adequate in order to be able to do the control loops that we're looking for. I'd like to hand over now to Dr. Peter Fussey, who will talk us through how we use this reduced model in order to integrate it into the control system, and then use the control system to optimize the vehicle response and make the system level improvements that we're looking for. Over to you, Peter.
Thank you, Dave. So to conclude the webinar today, we will consider how the thermal system should be controlled. The thermal system needs to take many, often conflicting requirements and select the best overall way of controlling the various actuators. In the past, with combustion engines, the system had a large source of heat from the engine, and the controller or thermostat was used to avoid high temperatures. As we move to electrified vehicles with less waste heat, we need to be very careful about how the electrical energy is used to heat up the vehicle systems. On the right, we highlight some of the trade-offs between the energy cost and emissions versus the cabin comfort and overall performance. For example, in a battery electric vehicle, a larger heater power can be used to warm up the cabin quicker. However, this uses up more stored energy, which has a direct impact on the overall vehicle range. Let's start by considering some of the challenges in developing thermal control algorithms. Firstly, for those of you who have developed control systems, you will appreciate that a system with delays or lags, as found in a thermal system, is harder to control, and you need to be careful to avoid instabilities. Secondly, with a thermal system, the thermal circuits can be divided up into many elements, each with its own temperature or state. As the number of states in the system increases, then solving the equations becomes increasingly difficult and can exceed the capacity of a control unit. Thirdly, there are several conflicting demands placed on the thermal systems to keep everything at the right temperature, but use the minimum amount of energy whilst delivering the performance the driver expects. And finally, as shown in the graphic, there is a question of limits or constraints. Adding a constraint to an optimization can make the problem difficult and expensive to solve. And this is one of the main motivations to use model predictive control. For more details, see our earlier webinar on the topic. Now, consider the optimization in a little more detail. As well as including constraints, the optimization can carry out the trade-offs we introduced earlier. Optimizations need a mathematical way of deciding what is best. This is usually done by introducing an objective or a cost function that is minimized by the controller. The choice of objective function is a key stage in developing this approach. For example, it could be the total energy used by the vehicle plus the temperature error. Looking at the formula here, our mathematical function is the integral of the power from the battery plus weighting factors multiplied by temperature errors. The weights are calibrated to change the priority of the controller. So small values of W will tend to reduce the significance of the temperature error and favor solutions that minimize the energy from the battery. You will have noticed we have an integral term. This means that we integrate the power from the battery and the temperature errors over a future scenario. To do this, we have to make an estimate of how the vehicle will drive, for example, from the telematics system. And then we use a model to predict how quickly the temperatures will change. The model simulates both the electrical powertrain to estimate the battery powers and a full thermal system to estimate the temperatures. So moving on to the application, Ricardo have developed a suite of algorithms called HEAT-R, Ricardo's holistic, efficient, advanced thermal controller. These algorithms are for multi-temperature thermal circuits and can be used to deliver efficiency benefits whilst reducing development times. I will now illustrate how thermal control can be integrated with the optimization of the energy in an electric vehicle. This case study considers a common challenge for the adoption of electric vehicles, that is, range anxiety or worrying about running out of charge. Electric vehicles have eco buttons and so on that can be selected to reduce energy consumption. But it would be better if the car itself could optimize the electrical demand from the thermal system to ensure that the vehicle can safely arrive at its destination. A prerequisite for this is knowing the future route, a feature that is becoming more widely available. This can include both the best estimate for the route and also potential traffic or disruptions as shown in the graphic on this slide. For illustration, in this case study, we consider a WLTP cycle, and to allow us to investigate the range anxiety, we consider 2 cycles to deplete the battery. The simulation is also run at 20 degrees C and 0 degrees C, with and without a couple of traffic jams, which are introduced as stationary phases during the journey. These are shown in the lower figure. The vehicle starts with a battery that is 25% full. And for the purposes of this study, the driver is assumed to get anxious when it falls below 5% state of charge. Finally, we need a measure on how to assess the thermal control. The thermal error has been calculated in the formula here as the integral of the error from the set point normalized by the set point itself. The optimization results are now presented in the following graphs. Here we have the baseline model at 20 degrees C with no traffic. The top left shows the vehicle speed, and you can see there's no traffic jams. The bottom left shows the battery state of charge, falling from 25% down to about 8%. This means that the driver is not yet anxious and range anxiety is shown as green. The light blue line shows the motor power in order to drive the vehicle. The top right plot shows the temperatures. The target temperature for the cabin is 21 degrees C, and the cabin temperature is shown in dark blue. The other lines are the system temperatures, such as the coolants in the different circuits. In this case, ambient temperature is 20 degrees C, so there is not much heating required, and the thermal error is green. The bottom right plot shows the powers in the system. In particular, the blue line is the PTC heater power that is used to heat the cabin. We also show the battery power and the heat recovered from the battery, and finally the cabin power showing the heat loss to the ambient. We now consider the same vehicle at 0 degrees C with 2 traffic jams. You can see the pauses on the vehicle speed. In this case, without using an electronic horizon, the PTC heater is used to heat up the cabin as fast as possible. The PTC power is shown in blue on the bottom right plot. Note that the PTC power is limited at the beginning due to the power limits on the battery at low temperatures, which also starts at 0 degrees C. The thermal error is greater now because we start off below the set point. However, this is still the best achievable with this hardware, so the status of the thermal error is still considered okay or green. However, the state of charge has now fallen below 5% and is causing range anxiety to the driver. So range anxiety is now red. With the same test case, we use the electronic horizon to predict the energy consumption required to power the vehicle for this journey. The remaining energy is used to heat up the cabin. The optimization trades the increase in temperature error with a reduction in energy demand, effectively finding a reduced set point for this specific journey. In the top right, you can see the reduced temperature target is now below 20 degrees C, with the power minimized in the bottom right plot. The battery is now kept above 5%, and the driver doesn't have range anxiety, whilst the optimizer has kept the discomfort to a minimum by adapting the temperature profile. The thermal error is now yellow to reflect this trade-off. I will now hand back to Dave for the concluding comments.
So thank you very much, Peter. So as you've seen from this brief introduction to Ricardo's tool set in this domain, we are able to take some high fidelity component models, join them together into high fidelity system or plant models, validate them against a baseline data set of a vehicle, then take those advanced models, reduce them down to a model that will run in real time on the vehicle, and then leverage the control system on that vehicle to be able to improve the efficiency of the systems by up to 25%. So I'd like now to hand back to Chris for any questions and answers. Thank you very much. Over to you, Chris.
First question I've got is, Peter, it's for you. Peter mentioned optimization. What techniques do you use to find the optimal solutions? Big question.
Thank you, Chris. Well, I did gloss over the details of the solutions just to keep within the time constraints of our webinar. But as I mentioned, we used a model-based approach, taking Dave's reduced order models to predict the responses of these systems. These models then form the basis of optimization techniques, such as optimal control and model predictive control. The results in the presentation were obtained using a MATLAB-based optimal control toolbox called GPOPs, which uses a large pseudospectral collocation approach, a bit of a mouthful, which turns the control problem into a large-scale optimization that optimizes both the control and the system response at the same time. So please look that up if you want to have a bit more detail.
That is quite a mouthful. Let's go through the questions. Cedric, I've got one for you. I know you're having a few issues earlier joining on, but right. How long does it take to gather the input data for vehicle thermal model with all of its components?
Okay, hopefully you hear me again.
We can.
Yes, thank you. So yeah, thanks for the question, Chris. So depending on the complexity of the vehicle and its thermal management system, it can take some days to 2 to 3 weeks in order to have a refined model. If the data of the 1D plant model are not available, we can use our own database. In Ricardo, we have a big set of data from components, respecting, of course, confidentiality, in order to assume and estimate the missing data. So, for example, the heat exchanger map, QITD, or an electric water pump performance curve, pressure head versus flow rate for different PWM control. So that will be that range between some days to 2 to 3 weeks, I would say, Chris. Thank you. Okay.
Thank you. Another one for you, Cedric. Do you recommend heat pumps for BEVs and or PHEVs?
That's a tricky one. It's always a hot topic, if I may say. The heat pump is for cold conditions, of course, hence the pun. But the limitation of the heat pump is of course, well known, around -10, -15 degrees Celsius with 1, 2, 3, 4 YF for now. So that means that it could be seen as an expensive component to be added to a vehicle, because we still need electric heaters below -10, -15 degrees Celsius. And in cold conditions, this is what we can get, of course, -20, especially in Detroit when it's quite cold. I've seen that once or twice. So the choice of the refrigerant is also important for deciding if we have a heat pump. So CO2 is a new refrigerant that will be coming to the market soon with one OEM, as I mentioned earlier in the presentation. The cost-benefit ratio of the solution is very important and needs to be studied, thanks to the approach that we have shown today. Reviewing the heating requirement and with the COP, how much benefit we get in terms of EV range. And that will be for the end user, that we will have to demonstrate the benefit. And I know, of course, the purchasing team in the OEMs will be heavily focused on the price of the heat pump. Adding just a valve seems to be simple, but it has a cost. You're reusing the waste heat from the electric components and not just sucking air from the air from the ambient and generating heat into the cabin is not the only approach. So direct, indirect heat pump needs to be considered. But we see more and more OEMs going into that direction, especially because of the EV range benefit for different countries. In cold countries, it will be obvious. If it is very cold country, it might not be as obvious. But I would say for the northern part of the US, that seems to be almost, for me as a thermal engineer, having some knowledge about cost, a no-brainer. So meaning that you need to have one for BEV. For PHEV, it's debatable because you have the engine heat that is available, and coupling the circuit with the engine could be seen as a good way to use the heat pump. But once we go into geofencing, entering the city, the towns, and we will have to drive in electric mode, the heat pump will be very welcome. And that will be part of the electronic horizon that Pete has mentioned. Geofencing will come, and it's already proposed by some premium luxury OEMs, and that means it will come mass market in the next 3 to 5 years.
Okay, thank you. Let's look at the questions that come in. Oh, Peter, one for you. The case study refers to warming up the vehicle. Are there similar benefits we found for cooling down the vehicle? I think you're muted, Pete.
Sorry.
There you
go. So yes, we have focused a lot on the warm-up, as there are obviously clear benefits to recycle heat to warm up other systems. However, for cool down, there are also some opportunities. First of all, there's new technologies to improve the AC efficiency, compressor efficiencies that are on the market and continually being refined. But then if we move on to the controller itself, there's potentially two areas where we may get some benefits from advanced control. Firstly, if we look at the subsystem level, and here we focus on the high power consumers, these can be managed to operate at higher efficiencies, although this can have limited benefits if the systems are already running efficiently. Secondly, we can coordinate the cooling down of the vehicle with the routes, so the electronic horizon. And we did this a couple of years ago by coordinating the air conditioning with the vehicle's stop-start strategy, allowing us to pre-cool the cabin a little before the vehicle stopped and the engine switched off, to then allow the stop-start strategy to have less of an impact on the cabin comfort.
Okay, okay.
Back to you today.
Other questions that have been coming in. Cedric, you talked in one of the slides about using the same fluid to cool the motor, the electronics, and the battery. Can you talk a bit more about that?
Oh yes, that's a topic I love. Thank you, Chris, for that one. So I mentioned earlier the use of the oil to cool the electric motor and the power electronics on the electric drive unit, and that is using the transmission oil, of course. I've mentioned also the battery that could be now using immersion cooling technique, using dielectric oil, dielectric fluid, but and especially potentially a dielectric oil. So why not envisage to have the same fluid to cool everything on the battery electric vehicle? Because the transmission, even if the manufacturing process has got some debris after the manufacturing, you can still have a filter, a magnet to catch all those debris and to avoid them to go to the battery. Could be seen as a holy grail for some people, especially in manufacturing and dealerships, because you will use only one oil to cool everything, to do the lubrication of the transmission. But of course, the drawback of the aging of the oil with the the transmission, lubrication, and the possibility to have debris that might go into contact of the battery cells, the bus bar, because we cool the bus bar also with that dielectric fluid, could be seen as a big break to adapt that solution of what I call the holy grail of one fluid for all. I think it's a possibility, but we will not see that right away on mass market. That could be maybe seen for niche application, sporty application, or race application also. Thank you.
Yeah, you mentioned immersion cooling there. We've covered this in other topics, but where are you standing at the moment on the immersion cooling? Is it partial immersion, fully immersion, splash? Expand on that for me.
Thank you, Chris. Yes. So immersion cooling is an interesting topic that we have started to work a long time ago, 10 years ago. But due to battery cell manufacturer warranty limitation, we didn't continue. Then 5 years ago, we restarted with dielectric fluid suppliers, but also OEMs. And now we have our own battery pack design for with immersion using dielectric oil mainly, but we use also chemical fluids. And that is exactly for different cell geometry. So we have cylindrical cells that was mentioned with the ICOBAT project from Innovate UK program, but also prismatic cells, pouch cells, we have our own design. The fact that it is a better cooling is now almost accepted by everyone than cold plate. And this is why we can go higher in C rate during ultra fast charging, but also for hybrid vehicle and sporty applications, we can go into very high C rates with power cells. There are still some questions about durability. Material compatibility has been done. Thermal runaway and safety is what we work on with dielectric oil suppliers because they are flammable fluids. But we are demonstrating that we can mitigate or even avoid the thermal runaway even with those flammable fluids because they have a high temperature flash point, and we will not have a catastrophic failure and a fire propagating into the fluid and outside the battery pack. So hopefully we will show that very soon in webinars just after the summer break. We are still in summer break, I would say, and hopefully you will see the benefit of the immersion cooling. And we think it will come to mass market in the next 3 years with the requirement for the ultra fast charging first. Although you see already some applications, hybrid sporty applications that are having at the moment battery immersion cooling, such as the McLaren Speedtail, which is public domain information since recently in June, it has been announced. So it's a really topic I love, and if you have any question about that, we'll be happy to help you to develop battery pack with immersion cooling for ultra fast charging and high performance applications, ultra fast charging for mainstream applications, of course.
Thank you. I'm just getting a few messages that some people are struggling to hear us. So if you are struggling to hear us, let us know. We want to know that any feedback on that. And coming to the end of our hour, any questions that are still coming in, we will get them back to you. We'll get answers and come back to you on that. And the webinar itself will be available. For questions, you have the emails on the screen there. Please come through to any of us. We'll see what we can do to get those back to you as quick as possible. So I'll say thank you to David, Cedric and Peter. Thank you for your time and efforts putting this together. Our next webinar for Ricardo North America is going to be a joint webinar with the Californian Hydrogen Business Council. We'll be looking at the next stage for fuel cells and a call that is coming out there. And this is scheduled for September 23rd. So I look forward to seeing you then. So say keep your questions coming in. Apologies if there are any audio issues. Thank you to the team and thank you very much.
Thanks a lot.
Thank you. Goodbye.
Thanks, everybody. Bye now.